Do you like to break things? Have you ever wondered how strong something really was? Because I had the same question, and I like to break things too. Hi, my name is Dominic, and this is how I built a tensile tester. But first, what is a tensile tester? They measure material properties by pulling things apart, equipped with sensors to measure how much force is used and how much something stretches. By looking at these measurements, we can figure out how strong and stiff different materials are. But there's one main issue. These machines off the shelf are extremely expensive. So instead of buying one, I've decided to make one. And for that, I designed the frame of the machine in Fusion 360. Once I had an idea of what I was going to make, I started the build. And here it went.
Fuck.
Finally, it was complete. A machine capable of breaking samples and collecting data. Well, not quite. First, I had to calibrate the load cell to get useful force measurements. But I couldn't find large enough calibrated weights for cheap, so instead I became the weight myself. Then for the first test, they didn't go according to plan. The plastic grips I made were not nearly strong enough. And as I was at school, I had no motivation to make a more rigid system, so this project stayed dormant until I headed home, where I dismantled the lower mount and began to fabricate an all-metal grip. By this point in the build, I felt that my welding skills had definitely improved, but let me know what you guys think down in the comments. I reassembled the machine, and it was time to test the new grips. Here I was confident that the samples would break, and the question was no longer whether the samples would break, but instead where the samples were breaking. To answer this, I iterated through several different designs, predicting my results in FEA and then testing the samples with my machine. At this point, the machine was capable of breaking samples somewhat consistently and measuring the force required to do so. However, there was no means of measuring how much the samples were stretching. So I attached two small clamps to a pair of digital calipers to measure the sample's elongation. Then I tested everything together. Here, things were looking promising, so I moved on to the electronics that control the machine and collect data during testing. I wired up the electronics and attached them to the machine. But what do those electronics actually do? Well, I'm glad you asked. There's the motor, sensors, and control boards. The motor moves the grips that pull the samples apart, and attached to the grips are the sensors, a load cell that measures force, and a pair of calipers that measure displacement. These measurements are then sent to a main control board. The main board takes in instructions from a handheld controller and also relays the test data to my computer via Wi-Fi. On my computer, a custom program graphs the measurements live and saves the collected data to a file. Then I made sure everything was working as expected. The only problem was the caliper mounting system. It was too bulky and got in the way. So I changed it and it was time for the first official test.
3, 2, 1, move.
From that test, this is the graph that the machine creates, which is cool, but in its current state, this is not very useful. To change this, we need to adjust our raw data to be more meaningful. First, we convert the force measurements into stress by dividing through by the cross-sectional area of the samples. Next, we change the length or displacement into strain, which is just how much the samples stretch. After adjusting our data, we get this graph, which has a similar shape to the original, just with a different scale. Now that we know how to get useful force measurements with the machine, it's time to do some more testing. To start, I printed out 15 samples in sets of 3, with varying infill percentages ranging from 10% to 30%. I then measured the width and depth of each of the samples to account for any variances from 3D printing. I also weighed them to see the amount of material for different infill percentages. I recorded these measurements and began testing. Here's some of the graphs from those tests. Visually, the data looks pretty good. That means there's only one more step before getting the material properties of the samples. There are two material properties of interest: the ultimate strength, which is how much stress the samples can take before breaking, and the modulus of elasticity, which relates the stress to the strain of the samples. Looking at a graph, the modulus of elasticity is just the slope of the linear portion of the curve, and the ultimate strength is just the maximum stress value. With a few lines of code, we can automatically calculate both material properties and visualize them on the same graphs as before. Now for the results. The infill percentage had little to no impact on the mass of the samples, resulting in relatively consistent values for both the ultimate strength and the modulus of elasticity throughout the tests. Qualitatively, the modulus of elasticity averaged out to around 220 megapascals and the ultimate strength at 37 megapascals. Similar results for the ultimate strength can be found online at around 36 megapascals, where the modulus of elasticity was consistently stiffer by a factor of 10. This was most likely due to the plastic grips deforming and in turn overestimating the elongation of the samples. How can we improve this design? One major improvement would be making the grips all metal to increase their rigidity. Another would be adding features within the grips to better align the calipers. Both should help with the accuracy of the strain and modulus of elasticity measurements. If you have any other ideas, please let me know down in the comments. In review, we made a machine capable of pulling samples apart with up to 5,000 pounds of force, automatically recording and saving test data, and obtaining decent material property measurements. Overall, I'm quite pleased with the results and the capabilities of this machine. With that said, what do you want to see tested next?